Hello everybody, today we're starting with a new topic. Today we will be speaking about nonlinear vibration. Okay, it means nonlinear vibration. It's a topic of the today video, and generally nonlinear vibration are connected with the nonlinear differential equation. That is why we need some efficient tools for solving such problems. And today I will show you some method which is called the Galerkin method. And it's a method of the finding approximate solution for some nonlinear problems. Okay, let's make some simple example. Let's do some simple example as something which will be focused on, and we will be dealing with some, like always, simple hanged mass, but this time that elastic connector will be given by some nonlinear formula which is given by the function s of x. And for example, some example of nonlinear case, it will be kx plus k epsilon x cube. It will be example of the nonlinear system, and then characteristic of such a problem will be as follows. It's visible that restoring force of that elastic connector is strong or weak, nonlinear. And governing equation of that problem will be as follows. Such a thing we have, inertia force due to the Newton's second law, and also we have the force which will be in that elastic connector. And of course, like always, we will divide everything by the mass, and we will get such a thing as a governing equation. Okay, and how the Galerkin method works. Firstly, we are introducing some differential operator which will be connected with that equation. I'm introducing the differential operator which acts on the x, which will be the solution. And in the case when the x is a solution, if the x, it will be the solution, x is solution, then L of x is exactly 0. But if, for example, if some different function x tilde is not solution, then our differential operator which acts on the L tilde won't be 0. And the difference between those things, it will be the residual value, which will be some estimation of the error. And of course, because that thing is a 0, that thing is not 0, or maybe it's only in the approximate way 0, then that thing cannot be 0. Of course, there is possible that there will be some points where it will be 0, but it's not true for all t's, for all t domain, time domain. Okay, and for that method, in auxiliary way, we are assuming that our estimated or approximated solution can be predicted in the form of the trigonometric series, something which will be similar to the Fourier series, okay? Maybe I will give it in such way, it will be the sine component omega I t plus also cosine component with the index index I, which denotes the subsequent elements of that series. Okay, and it will be from the I equals 1 to the n. Okay, and then if we assume that the solution can be predicted in that form, then also the value of that operator, the result of acting of the operator of the predicted solution will have the same form. It's obvious because, for example, even if we are taking derivatives or some powers of the trigonometric series, we are getting almost the same form. Of course, the numbers will be different if we are talking about the coefficients, but the form will be almost exactly the same. I mean, it will be given by the form of the Fourier series. It means it will be given, for example, by AI times typically cosine omega it plus bi times sine omega it, which is similar to the form of the Fourier series. Okay, and now we will be looking for the value of the minimal value of such a functional which will be based on that difference. Okay, I mean, we are introducing some function, let's say v, which will be some kind of the measure of the error, I mean of that residual value of the difference between L of x tilde and L of x, where the x is an exact solution. I mean, we are taking the difference as an error in time. To omit the negative values of the error, we are taking square, because square ensures that we are dealing only with the positive values, and also because we want to estimate the total error of the difference between the operator which acts on the predicted simplified solution and exact solution. We will take the time integration process, because by that approach we are summing the particular errors which are positive to the square sign of that thing. Because that thing will be 0, we are dealing with such a thing. I mean, that thing is always 0, because operator L, which acts on the exact solution, gives us 0. I mean, we are trying to minimize such a functional v. Okay, and of course, it will be that v will be parameterized by the AI and BI coefficients. I mean, it will be such a function, because of course it won't be function of time, because process of the integration will remove time from our problem. Okay, I mean, we are looking for the situation where that estimated value of the error will be minimal. How to find it? We know that thing, because from the calculus we know that if we are looking for the minimal value of some functional, we have to consider the system of the following equation. I mean, we have to compute the first derivatives due to the system parameters, I mean due to the system variables, to get the conditions of the minimal point or the critical point. Okay, and let's try to do it for our simple functional. It's easy, because if we are dealing with such a thing, we have to compute the partial derivative of our functional, our integral functional. It's not a function, because there is some difference between the functional and function. And because integration is over time, we can put the symbol of the partial derivative inside the integration sign. I mean, we are dealing with the partial derivative which acts on the square of our differential operator, which acts on the x tilde, and everything will be integrated by dt. And in the next step, we are computing the partial derivative of such an expression, and we see that it will be integral of t times 2, because here we have the external derivative in the form of the square, and there will be L of x times d over d ai, which acts on the L, which acts on the x tilde, and everything will be integrated over the time. Okay, and what we get? Look, that thing, it's our differential operator which acts on the predicted solution. It's nice because we have such a thing. And if we are talking about the partial derivative of that thing due to the system parameter, we have to take that formula, where the AI and BI are the linear coefficients of that expression. Okay, that is why I will rewrite some inclusion. I mean, now I am computing only that part to put everything into integral. I mean, it will be such a thing. It will be integral of the sum from the I1 to the N of the A. Sorry, I have to change the index, because look, if we have the I here, it will be some kind of the parameter. That is why I will be summing over the J this time. And it will be J cosine omega J T plus Bj times sine omega J T. And everything will be taken in the parentheses. Let's compute that derivative. And look how it works. If we are talking about that components, it will be exactly 0. Okay, but if we are talking about the first component, here we see A1 times cosine plus A2 times another cosine. I mean, approximately we have as that part of that sum, we have such a thing. It will be 0 as that component. Here we have such a thing. I mean, here we have A1 times cosine omega 1 t plus A2 times cosine omega 2 t through the our Aj AI times cosine omega it and the rest of the elements of that sum. How it works? It's visible that if AI acts on the A1, it will be 0. The same in that case. The same of that elements which will be hide under that multiple dots. And there is only the one situation where that derivative will give us non-zero result. When the partial derivative operator which acts on the AI component. It means that through that entire process we are getting only the cosine omega I t, nothing more. Okay, it means that if we put our results to our integral functional, we are getting that it's a 2-time integral over the period of our predicted form of the solution and times only the cosine omega I t, and it will be integrated by time. It is the condition where such a functional get the 0. Exactly the same situation will be for the integration with respect to BI. And as a result, we take such a condition. I mean, the 2 times integral over the period L of x part times sine this time, because BI is connected with the sine component. And it will be over dt. 2 simple conditions for that element. Of course, the entire process is for the I from the 1 to predicted number of the components which are taken into account for our simplified form of the solution. As you see, it isn't especially complicated. We are getting only 2 simple conditions which indicates the minimal value of the parameters, which give us minimal value of the residual function error. Thank you for your attention, guys. See you next time.